Have you ever stopped to think about how a massive database, we're talking billions of records, can find the one thing you're looking for in less than a second? It feels like magic, right? But it's not. It's actually a really beautiful piece of computer science. So let's pull back the curtain and find out the secret that makes so much of our digital world tick.
I mean, seriously, think about that question. How is that speed even possible? Imagine I handed you a phone book with a billion names and told you to find John Smith. You wouldn't just start at the letter A and read every single name, would you? Of course not. You'd use a smarter strategy. Well, computers need a smart strategy too. And that really gets us to two very different ways of searching. Over in the slow lane, you've got what's called a linear search. This is the brute force way, literally checking every single item, one by one. But then you have the express lane, binary search. Instead of going one by one, it's way smarter. It chops the entire search area in half with every single guess. The difference in speed is just, it's not even a fair fight. And this whole divide and conquer idea is the key to everything. Now, to make this super fast binary search happen, a simple list just won't cut it. We need a hero, a special kind of data structure that's built for this kind of speed. And this hero, it lives by one simple golden rule. And that hero is the binary search tree, or a BST for short. So what is it? Well, it's a data structure that looks kind of like a family tree. But here's the magic, that golden rule. For any spot on the tree, anything that branches off to the left has to be smaller, and anything that branches off to the right has to be larger.
That's it. Seriously, that's the entire secret sauce. This one beautifully simple rule is the foundation for this incredibly powerful and efficient structure. Let's see what that actually looks like. And here it is, that golden rule in action. Pick any number on this tree. Look at the root, 56. See how everything to its left is smaller and everything to its right is bigger? This strict, simple order is what gives the tree its superpower.
Okay, so we've got the rule. But how does that simple idea actually lead to lightning-fast searches? Let's, put this thing to the test. All right, we've got a mission. We need to find the number 27 in this tree. Now, instead of just scanning around randomly, the BST is going to use its golden rule to make a series of really smart decisions. Let's follow the path it takes. Okay, here we go. We always start at the top, the root, which is 56. Is 27 less than or greater than 56? Well, it's less. So, bam, we just eliminated the entire right half of the tree. We go left to 26. Okay, now what? Is 27 greater or less than 26? It's greater, so we go right to 28. And one last time, 27 is less than 28, so we go left, and boom, there it is. We found it. Think about what just happened. It only took 3 little comparisons to find our number. With every single step, we threw away half of the remaining options. Now just try to scale that up in your head. With a billion items, a nice balanced BST can find any single one of them in about 30 steps. 30! That's insane! That is the secret to how databases are so mind-bogglingly fast. But, like every good hero, the BST has a weakness. A kryptonite. There's a villain in our story that can show up and steal all of its superpowers, and this is where things can go really, really wrong. This quote right here gets to the heart of the problem. It turns out the tree's performance, its shape, depends entirely on the order you put the data into it. If you add things in the wrong sequence, you can get what's called a degenerate tree. And this table just shows you how bad it can get. In the best case scenario, when the tree is all balanced and bushy, our operations are what we call O of log n. That's our lightning-fast express lane. But in the worst case, when the tree gets unbalanced, performance just tanks, all the way down to O of n. We are right back in that slow, inefficient, one-by-one linear search. And this is what that nightmare scenario looks like. On the left, you've got that beautiful, efficient tree we want. But on the right, if you add data in just the right, or I guess wrong order, like sorted numbers, the tree just turns into this long, pathetic, spindly chain. It's basically just a glorified list, and all that amazing speed, poof, gone. So how do we stop this from happening? How do we protect our hero and guarantee that incredible speed? Well, of course, computer scientists came up with a really clever solution. They invented a smarter kind of BST. Think of them like a BST 2.0. They're called self-balancing trees. They still follow that same golden rule we talked about, but they have a few extra tricks up their sleeves to stay in shape. So here's the big idea. These special trees, like AVL trees or red-black trees, they actually monitor themselves.
If you add or delete something and the tree starts to get a little lopsided, it automatically performs these clever little shuffles and rotations to rebalance itself. The whole point is to guarantee that it never turns into that long, spindly chain. It's a promise that it will always stay in that O log n express lane.
And you know, this isn't just some abstract concept from a textbook. This powerful structure is humming away behind the scenes in so many of the technologies that you and I use every single day.
Seriously, their fingerprints are everywhere. That crazy fast database indexing we started with? Yep, that's a BST at work. The way a character in a video game finds the quickest path through a level, that often uses a tree-like structure. From the way your code gets compiled to how your files are compressed, this elegant data structure is a hidden workhorse of our digital world.
At the end of the day, that's what binary search trees are. They are a fundamental building block of modern computing. They're the silent, incredibly efficient organizers that take a whole mess of chaotic data and give it a beautiful structure that unlocks unbelievable speed and power.
And it all comes back to that one simple idea. Left is less and right is more. A rule so basic, yet it powers so much complexity and efficiency. It kind of makes you wonder, right? What other simple, elegant rules are out there, hiding in plain sight, running the rest of our digital lives?